which was measured using the I-square. So today we'll start with the binomial, that's the odds ratio when you have got the 2 by 2 table, and then how can you perform the meta-analysis in JAMOVI. So in the first, before this breakout room activity, I will demonstrate it on JAMOVI. And once you guys practice over this JAMOVI, then we will show you the RevMen. And then again, if time permits, we may have one breakout room activity for the RevMen also, because we explored RevMen to some extent, and then again we are finding that it has got beautiful features. So, but for that, first learn JAMOVI, and then you can also increase your learning curve towards shifting to the RevMen. So I'll first start with the presentation of this odds ratio, because we will see the meta-analysis of all the effect sizes. So this is, before that, let's see the question. So we have shared these files with you people. So this is of the meta-analysis of the dichotomous outcome. And dichotomous outcome, the various effect size, which you can use in case of a dichotomous outcome, can be the risk ratio, can be the odds ratio, it can be the risk difference, or it can be the, these are the main 3 types of risk measure or defect size in case of a meta-analysis of dichotomous outcome. So the background is again like acute diarrhea. It is a major cause of morbidity, especially in the low-income countries. That's just the write-up which is giving the background setting of this research question or the review question. And then several randomized control trial. I'm reading this section right now. Like several randomized control trial, they have compared the proportion of children who had diarrhea on or after the 4 days between those receiving probiotic as compared to the standard treatment. So here the binomial, I have categorized, or I have taken the data from the studies who are reporting the persistence of diarrhea at or after 4 days or 96 hours. Because if you can recall the last session, we have converted the days into hours. So 4 days means 96 hours. So diarrhea, if there was a diarrhea on 4th day also, that we are treating it as a positive outcome, and in both the standard treatment group as well as the intervention group. And then coming to the review question. So the review question was like, in children with acute diarrhea, the use of probiotic as compared to the standard treatment alone, reduce the proportion of children who continue to have diarrhea beyond 4 days of illness. So that's my review question. That means, does the use of probiotic reduces the proportion of children who continue to have diarrhea beyond 4 days of illness? So that's my review question. So let's see first how I have gathered the data, or how from the study, what all table I have seen to collect this data particularly. So this we have taken the snip from those studies where we could find these 2 numbers. So I need number in the control group and in the intervention group of the children who are still having diarrhea at 4 days. So this was the first study by the Din Lesai 2014, and the title of that study was the Lactobacillus reuteri effectively reduces the duration of acute diarrhea in hospitalized children. So if you see here the percentage of children with diarrhea, this is the 90. Again, I said that 4 days is 96 hours. So he has given it in the intervention group is the Lactobacillus reuteri, and the control group is the standard treatment. So he has given both the number. So if you see, 11 children out of 64 are having diarrhea at 4th day. And in case of a control group, 22 children out of 63, they are having diarrhea at 4 days. So that I'll show you the table, also the Excel sheet where we have entered the data. That's how you have to enter it. So this This for that, the basic requirement is first thing. Before you start with meta-analysis, you should be well versed with all the basic statistics and epidemiology method. Because if you are not well versed with that, it will be difficult for you to see these things and to understand what is variance, what is standard deviation, what is confidence interval, what is this thing, correlation, what is association. So these things, what is effect measure, what is effect size. So these concepts are needed, because in whole of this meta analysis you will see that we are using these terms quite often. So those concepts, we cannot build it in a day or two. But again, if you start doing it, maybe you can go retrograde. That means whenever some terms come, you can go back and see it again, and you can keep on seeing those terms repeatedly, so that probably at the end of 1 year or so, these terms will be familiar to you. And you should know only that much which is of your relevance. Because everything, if even if you know how to interpret it, what is the basic understanding of these terms, that is okay. And from study, you should be able to gather these data. So that's why I said that you have to, when you are doing the systematic review, you have to read each and every study very meticulously. So even if you are using AI for data extraction, that's, I mean, after reading it thoroughly, you can take help of AI. But if you don't read studies, then these finer nuances or finer detail, AI cannot do it for you. So that's why we encourage all of you to read thoroughly the final included studies. And generally, that is not many. Many means generally research question, or you may start with a review question which does not have too much of literature, the included study. So let's say if it is 25, 30, then like you need to read it. So that's why these numbers you can extract from the studies which you have included finally in the synthesis, the quantitative synthesis, which is the meta-analysis. Again, this is the study by Khan, which is the clinical efficacy of use of probiotic, and the strain of probiotic which he has used is the Saccharomyces boulardii in children with acute watery diarrhea. And if you see the frequency in table 2, he has mentioned the total number of children were 420. That means 210 in each group. And on fourth day, all 210, they were not having diarrhea. So if you see the outcome here the outcome is not the persistence of diarrhea. Rather, the outcome is like less than 3 stools per 24 hours. That means we have defined diarrhea using the WHO criteria, having stools more than 3 stools in 24 hours. So if all the 210 people, like they are having less than 3 stools, that means on fourth day, none of them is having diarrhea. That means it is zero. If you take the example of the previous, then LSI, there they have shown the number of children still having diarrhea. So here, what they have reported, it is less than 3 stool. That means no diarrhea. And again, if you see this number, 180, they are having no diarrhea. That means how much is having diarrhea? So you have to deduct this number from 210. So it will be 210 minus 180. So 30 children are still having diarrhea. Am I making myself clear how you can deduce these numbers from a study? Many times it may not be there directly. You may have to do, but you see, it's very minor calculation. You don't have to do very huge calculations. It's a very minor calculation, but you have to be meticulous seeing these things there, because you can then make error. I'll show what error we made initially. So this was the again from this Khan. Again, if you see this terrain. So terrain, initially we extracted the data from the terrain also. But later, when we have seen it meticulously, if you see, initially we have just seen that it is day 4, and he has giving it like 5 out of 25 is having diarrhea at 4, and in both in the probiotic group it is 0. But if you see here, it is the stool output. It is not the diarrhea, persistence of diarrhea. Or in this case, he has given the persistence of vomiting. But that data, the persistence of stool at 4 days, that he has not given. So this study, I had initially, what error we made, like we took this number, but this cannot be there in our meta-analysis. Why? Because the outcome which I am considering now, this author, he has not reported that outcome. So now you will see that I will exclude this study from this final, uh, you know, dichotomous, which I have just shown you, like odds ratio, risk ratio as effect measure. This I will not take. Then coming to the next, which is the DIL-SI 2015, because initially we have seen DIL-SI 2014 and here the DIL-SI 2015. So he has reported like two studies related to this, and here if you see, he has reported that this Saccharomyces boulardii. And again, if you see the title of the study, it is this table. So it is the percentage of children with diarrhea in the whole population. So it is the percentage of children with diarrhea. So this is clear cut. And this is again 96 hours. So if you see, it is the fourth day. So 37 children out of 220, because total N, you need this N in the intervention group and N in the control group. So if you see N in the control group, it is 143, and in the intervention group, it is 220. And here it is out of 143, 39, they are still having the diarrhea children. And out of 220, 37, they're still having the diarrhea. So this is we took these numbers, and again, there was a study of Francavilla. And if you see the Francavilla again, if you see the title, number and percentage of patients with watery diarrhea at days of treatment, at days, and we have taken at fourth day. So if you see this is again same outcome which I am studying. So out of total, if you see this 35, so out of 35, 14 are having. So this bracket, this is the percentage. You cannot take this number as total, because total he has written on the top. So N is total here, and in case of a placebo, this N is 34. And here in case of a lactobacillus reuteri, this 14 is the in the intervention group who are still having the diarrhea, and 17 in the control group still having the diarrhea. So these two numbers we have taken. Similarly, in the study of Ritchie, if you see, this is the table, secondary outcomes of aboriginal children with diarrhea disease treated with either probiotic or placebo. So first you see the total number. So the total number in the probiotic group, it is 33 here. So this N you can take from here. And in placebo, it is 31. So you can take this number from here. Again, if you go down and see this, we have just highlighted this with a purple color. So diarrhea on or after day 4. So here you can see 8 children out of 33 and 7 children out of 31. They are having this diarrhea at 4th day. So this was like total of, initially we took 6 studies, but you saw that in Terran, it was the stool output. In the median and IQR, it is not the diarrhea. So that's why we deleted that. We will delete that study. So this was regarding how you can extract the data from the existing literature, from the table, which or whatever article you have included. And then I'll show you how to do the meta-analysis in this. So I'll go, there's a data file which we have shared, and this is the event number. So this is the dichotomous outcome. So I'll just click this. First, I'll show you the Excel sheet. So you can see this we have entered using the JAMOVI, because in JAMOVI, I'll show you, it is the first is the number in intervention, event in intervention and event in control, then total number in intervention and total number in control. So I'll just show these two parallelly so that you can appreciate how you will enter the data. So these two, I'll go to the first slide. So if you let me. So this was the first study. You can see here 11. So 11 I have taken from here, 11 by 64. So 11 in the intervention group and 22 in the control group. This 22 I have taken, and then 64 and 63. So this I have taken from this 64 and this 63. This I have entered here, number in intervention and number in the control. And this is the format according to JAMOVI. Because in RevMan, actually numbers are same, but you know, the placement of column, here the first variable which you have to enter in JAMOVI, it is the event in intervention and then event in control. But in RevMan, it is just like first event and then total number. We will see that. So you only need to like make these column before or after, or otherwise number will be same. And we have shared the RevMan file also with you, but because we have just shifted it, so you can see and you can appreciate what is the difference between the data entry if you are using JAMOVI and if you are using RevMan. So let's now first focus on JAMOVI. We will talk about RevMan during the like second part of this session. Coming to the second one, which is the Khan, if you see, like I said, that all 210, they have recovered. So here I have entered 0. If you see this number, I have entered 0 here because in case of the second study, none is having, there was no event in the intervention group because I have defined event as the persistence of diarrhea on 4th day or after. That's why there is no diarrhea. And total number was 30 in the control. You can see here. So this was the 30, which I was talking, like 210 minus 180. So this is like 30, and then 210 number in the intervention group, and then 210. If I slide this later, this 210 in the control group, which I took like total is 420, and in methodology they have mentioned that they have taken equal number. So that's why 210 and 210 in each group. Then coming to the third study, this one, this I said that it is by mistake. So that's why I'll delete this. So probably what you can do, you can click this and you can delete this. Then coming to the next study, which is a Delnasi 2015. So this is there. So 37, if you see the total number, this is the 37, and then out of 220 and 39. So I have written 37 and 39, and then 220 is the total number in case of an intervention group. So these two numbers, 220 and 143, I have taken from, this is 220 and this is 143. Then again, coming to the next study, which is a Francavilla. So now I'll again show you how we have entered the data for Francavilla. So this is Francavilla, event is 14. So 14, you can see this number. So this number and this number, 14 and 17 and 17. And then if you come here, 35 and 34. So these two, like 35 in the intervention group, total N. This is the total N. And 34 here. So 35 and 34. And then going to the last one, which is the Ritchie. So coming to Ritchie, although the font is, it is, because since I'm showing it into this thing, let me, this one. So you can see 8 and 7. So these two are the numbers, 8 and 7. And then if you see the total number, 33 and 31. So these two numbers, 33 from here, probiotic group, and 31 here from the probiotic group. So this is the Excel sheet. So have you understood up till this point how we have entered the data from the table, seeing the outcome, taking the total n in case of an intervention and control group, and taking the event in each of these. So this is the most important activity once you have like decided that you have to start with the meta-analysis. That's because this takes time. For this, you have to sit, you have to read, and then you have to enter it. Again, the important thing is that like there will not be many studies. So that's why it is not like you have to enter 50 or 100 data. You have to enter only 4 or 5 column, that too limited number of studies, like let's say 10, 20, maximum 25, 30, like that. Okay. So that's why, but again, it takes time and you have to be a little patient when you are doing it. Otherwise, you may make errors. Right. So I don't know. Have you understood up till this point? Then only I will go to the JAMOVI and I'll show how to do that in JAMOVI. No chat, nothing. Okay. Okay. Yes. Thank you. Then I will go to.
Ma'am, shall I ask a query?
Please.
Ma'am, for registration of a meta-analysis,
Yeah.
if I have not done, say, I have started a meta-analysis 7 months back, but I have
Mm-hmm.
not registered in Prospero.
Mm-hmm.
Now, because I didn't know anything about that at that time. So
Mm-hmm.
now if we have to register again, is it possible or is it
Yeah.
not possible?
No, you can register it. No problem.
Because I'm almost like I'm done with the analysis. Is that okay? Because
That's
uh,
that's
okay.
okay. Still you can do it. And you can like what right now, whatever is the stage. I don't know whether you can write it like you have done it. Maybe you can again update it later, few months, because if you're planning to do the publication now, are you do?
Yes, ma'am. Yes.
But they will ask for it, and I think so. You can like wait for few days. Maybe this detail like is there any criteria that that much time should elapse between registration and start? But I
Uh,
think if you can what I will suggest that you get it registered. Okay,
okay, ma'am.
writing everything, protocol and everything, the detail of the Prospero, your author and everything, and then you go for publication. And
Okay,
if they like raise this issue, like they may not raise because they only see the number of your
okay,
Prospero registration, like they ask for IC registration number.
okay,
Generally, they don't check with the date, like how much time was there
Data
between the.
extraction needed. When they will ask stage, you will just say ki we are in data extraction phase. Then it will start. If you will mention that data extraction has completed, then your registration will be rejected. Just
okay,
click on data extraction under progress. Then also
okay,
wait
okay,
month, one means few weeks, 2 or 3 weeks. Then update ki data extraction done. Then it's okay.
okay, sir. Okay, okay.
Okay.
And is there any other platform other than Prospero, ma'am? Similar.
Many.
There's open
We will
science
share.
framework also. You can register
We will
there
share
also.
that. We'll share other platform.
Does it carry the same value like Prospero?
Yes.
Yeah.
Okay, ma'am. Thank you, ma'am.
Any other question? Dr. Farzana is asking, please you share the drive link where I can find all the SRMA workshop material. I know you have shared earlier, but I'm not able to find where I can find all the material. Okay, Dr. Farzana, we will share it again. So if this much is okay, we will go to the JAMOVI. So this is the JAMOVI sheet. And in JAMOVI, we have, like that day we discussed, I think there was some chat going on this thing, WhatsApp. Dr. Shamshad has also checked regarding the recent version. And I too downloaded that 26 version, but that has got some issue with this number. and that current version also. So what we did, we deleted all the files and then we only kept this 28 version, this thing. I'll show you. And I'll remove this analysis.
This new version is not including zero. If we have in the event number, if we have zero, it is not including one. But that older version,
But
2.3 version is including.
no, Subhapriya, but I tried keeping one also. Like we in this zero also that day, like we kept trying for like 1.5 hour. We tried changing the numbers. Even if you make it a non-zero, then also it was like showing some error, resource limit hit maximum, or all those
Yes, ma'am. Yes.
error. It was showing it up.
Yes,
Maybe there is some issue. Dr. Shamshad has written a mail to the person who has drafted this meta-analysis module. So probably they will look up into this matter, why this error is there.
Okay.
But again, for the time being, what worked best for us, like it is this version, which I
Okay.
was.
Okay.
So this version. Just a second. Version you can check with these 3 dots, because many times when you have got 2 to 3 version, you should check before starting. So this version 2.3.28, this version, it was working well. So now you see here I have to remove this terrain also, because terrain by mistake I said that we have included the stool output, which was not our outcome. So I'll delete this. You can click this and then it will be deleted. So now I have got 3 and 2 5 studies with me to check for this summary effect of binomial. So how I'll go? You go to this major module, click on this major, and here you can see we have discussed that day this option, mean differences. And then this effect size, we will discuss it today, but currently we are going with this dichotomous model. So because I have shown you that question, it is like risk ratio, risk difference and odds ratio that is there for the dichotomous. Dichotomous means each variable you have categorized it into 2 binary outcome. So here, what is the binary outcome? There are two group of intervention, like there's a standard treatment and there's an intervention. That is again binary type of group. And the other binary is number of children still having the diarrhea at or after 4 days in both the group. Okay, so this is and then you have got the total number. So out of total, how many are having the diarrhea? Coming to this, clicking the major, clicking this dichotomous model. If you click this, you can see here it started with study. So study you have to enter and again change this. Like again, Dr. Madhu and Dr. Subhapriya, they were also discussing regarding the changing these variables. So yes, you have pointed it out rightly. So here study variable, that should be categorical. And then event in the intervention group. So I'll move this value here in the event of incidence in the experiment group, event in the control group. So number of incidents in the control group. Then again, total number, total sample size in experimental group, that is the total in intervention, and the total in the control. So the way it is there in JAMOVI, the sequence, like it starts with the incidence in the experiment group, then incidence in control group, then total sample in the experiment group, and total sample in the control group. And that's why we have arranged the data like this. So if you see this Excel sheet, because then there will be no problem. You can directly import it in, otherwise you will have to see which variable it is asking, and then you have to move it accordingly. So if you do it like this, event in the intervention, then event in control, then total number in intervention and total number in control. So it falls at right place here when you have to enter these variables. Now coming to model option, we have discussed that day that model generally, what model we use? Generally we use this Dar-Simeon-Layard model. And here There are various measures. In dichotomous, like I discussed, you can use the log risk ratio, you can use log odds ratio, you can use risk difference also. These two we don't use, like transformation and all. But again, most common is the log odds ratio and the risk ratio. So we are demonstrating it with log odds ratio. So that is by default. Even if you don't do it, this takes log odds ratio. And then here I'm not doing any moderator analysis. And again, since this, what it does, basically whenever it enters this 2 by 2 table, it enters this in the form of a log odds ratio. So first I'll show you the interpretation also. And if you see the plots, plot is again, right now I'm only showing you whatever is there as a default, and then we'll see. So if I see this again random effect model, because we discussed that day what is a fixed effect model and what is a random effect model. So fixed effect model is generally when you consider that there is a no heterogeneity, and whatever studies you are taking, that is related to a relatively very similar geographical area, similar sort of intervention, similar study group. So PICOT, which we discussed, like population, intervention, control group, and outcome, they are quite similar. But you will often observe that in meta-analysis, that much similarity is never there, because it is generally there will be difference in population, age group difference will be there, intervention will also be different. In this case, only you have seen that there is a Saccharomyces boulardii. Many people have used the Lactobacillus reuteri, and then there are too many species, the dose of those group, and then how they are assessing the outcome. So all these, there will be a lots of variability. So I said that Borenstein has also suggested that in health, usually you should go with the random effect model, because fixed effect generally you will not see. But again, like we have seen that day, if the number of studies are less, like Subhapriya was doing only with 2 studies, then in that case, your fixed effect model, because with 2 studies, you expect that there will not be heterogeneity. And that random effect model we have discussed, can you recall we discussed that day between study variance, like tau. So that tau will not be, significant in case of only 2 studies. So whether it is random effect or a true or a fixed effect model, the result will be same if the number of studies are 2. So in this case, if you see, this is your random effect model where the total number of studies are 5. This minus 0.70, this is the, if you see, this is the estimate with the standard error, and this is the p-value. And this is the model. Model means it is giving you the in this 0.70. So what is this 0.70? If you see this, this 0.70, this is again the same value, 0.70 with this of the confidence interval. Now coming to, this is again, what is this? If you see, what is this? So this is log odds ratio. Because model measure, remember we have discussed this is the model measure, and this is your log odds ratio. This is not the odds ratio, this is log odds ratio. So how the JAMOVI gives the output? The JAMOVI gives the output as a log odds ratio, but how will you interpret the log odds ratio? So you need something in the odds ratio, because we know how to interpret odds ratio. So for that, there is an option here in JAMOVI when you can back transform log odds ratio as odds ratio. So can you see this here in this case? So this you can click, if you click this, it back transform log odds ratio to odds ratio. So click this. And then if you go up, let me see where it comes. Fail safe. Okay, it did not got clicked. It comes above, just after this heterogeneity statistics. So you see that odds ratio is 0.50. It is like this. And you know that those of you who have attended the logistic regression, you know that if the value of this log odds comes in negative, that means the conversion of log odds to odds will be less than 1. So here it is 0.5 with the 95% confidence interval. That means it is saying, how do we interpret 0.5? That the pool estimate is showing that this incidence of this diarrhea, persistence of diarrhea, it is 0.5 times less than in the intervention group as compared to the control group. If you want to express it in percentage, you know how to interpret. There are 50%. What do you do? 100 minus this 50. So there are 50% chances of experiencing diarrhea on or after 4 days in children of the probiotic group as compared to the standard treatment. That's how you interpret the pool estimate or the odds ratio with the 95% confidence interval. And this is significant. Why? Because it doesn't crosses the 1. So that's why it is significant. Now coming to the heterogeneity statistics, if you see the I-square is again, it is like moderate. We have seen that 25 to 50% was the 50 to 75 is the high and 25 to 50. So again, up till 75 it is okay. So heterogeneity I-square is 54. Tau, what was the tau? Tau was the standard deviation of the pool estimate. So this was the tau, or tau was also, we have discussed that day, it is the between study variance. Because in case of a random model or the random effect model, you consider that all the studies, they have a different true effect size. So there will be between study variation. So this tau is the measure of the between study variation. That's why we say that is the standard deviation of the true effect size. And then if you make it as a square, so you know when you square the standard deviation, it is the variance. So this tau square is the variance. And this I-square is the Higgins I-square. And we have discussed that day how to classify it. So up till 25%, it is the like low level of heterogeneity. 20 to 50, it is the moderate. 50 to 75, it is high. And more than 75, generally you should not perform because it is very high level of heterogeneity. Then comes your Q statistics, H square. H square is again measured, its value should be 1. So if the value is 1, that means there is no heterogeneity. If it is more than 1, that means there is a heterogeneity. And this Q statistics, if there is a, this is not significant. If you see, the value of P is more than 0.05. That means you say that the heterogeneity is not significant in case of this analysis. And that we have seen. Then again, one of you can read this so that we will see. That day also we have read this part. So yes, can one of you can read this? This JAMOVI gives like by default, but it gives only for dichotomous and mean. For others, you will see that it doesn't give you this write-up. Yes, can someone read this?
Yes, ma'am.
Yeah, please.
The analysis was carried out using the log odds ratio as the outcome measure. A random effects model was fitted to the data. The amount of heterogeneity tau square was estimated using the Der-Simonian LAD estimator. In addition to the estimate of tau square, the Q test for heterogeneity and the I-square statistic are reported. In case any amount of heterogeneity is detected, that is tau square is greater than 0, regardless of the results of the Q test, a prediction interval for the true outcomes is also provided. Student taste residuals and Cook's distance are used to estimate whether the studies may be outliers or influential in the context of the model. Studies with the standardized studentized residual larger than the 100x
You can skip that. A percentile, you can start reading from like percentile of a standard normal distribution.
Percentile of standard normal distribution are considered potential outliers, that is using a Born-Ferroni correction with two-sided alpha is equal to 0.05 for case studies included in the meta-analysis. Studies with a Cook's distance larger than the median plus 6 times the interquartile range of the Cook's distance are considered to be influential. The rank correlation test and the regression test using the standard error of the observed outcomes as predictor are used to check for funnel plot asymmetry.
Thank you, Dr. Geeta. So this was for you can, that day also we discussed that you can write this as a part of your statistical analysis, how this JAMOVI is analyzing it. And again, it is giving you the result here. So you can see this, I will read only the observed log odds. So if you see, it is writing that the observed log odds ratio range from minus 4.2 to minus 0.9, with the majority of estimates being negative. And the estimated average log odds ratio based on the random effect model was 0.69 with this range, and there is an average outcome differed significantly from 0. The Q test was not significant, but some heterogeneity may still be present in the outcome with this, because I said that I square was there, so some amount of heterogeneity is there. But again, since the p value of Q is 0.06 here, if you see this, it is 0.06. So that's why it is not very some amount not significant. And then 95%, the prediction interval, I'll see, I think I have not clicked it, but 95% prediction interval. And what we discussed about the prediction interval, it tells you about the future studies. So if any other future studies will be conducted on this topic, the true effect size might vary between these two values. Hence, although the average outcome is estimated to be negative in some studies, because there are some studies in the prediction interval is showing that some studies are showing the effect size as positive also. So that's why some studies, the true outcome may in fact be positive. An examination of the studentized residual revealed that none of the study had a value larger than 0.25. Hence, there was no indication of outlier. So in this case, that's why we will not perform any sensitivity analysis the way we did for the mean one, because mean, remember, we removed few studies and then we performed the meta-analysis and saw that there was a less of heterogeneity when we removed few studies. So, but that we are not doing in here, because there is no heterogeneity. But again, it will guide you. If there is a heterogeneity and a potential outlier or influential point, you can exclude that study from your analysis and you can see. And you can do this write-up in your meta-analysis part. This we have done back transformation, display model fit. Prediction interval, if you click, it will show in the graph. If you come and see the graph, it is like, it is the prediction interval. So the diamond, this value is the summary estimate. These two edge, they are the confidence interval of the summary estimate. And these two, this one and this one, this is your prediction interval. It is not very clear here. When you will see that Revman, it is more clear there, the prediction interval. But again, with dotted line, you can see here also. And when you click this model fitting weight, it will show you the value of like weightage, relative weight of the each study. So you can see here, this tells you the relative weight, 24%, 32. So largest, this del SI is having the largest weight. And that day we discussed that this size of the square, it tells you the weight. So the larger the square, the more weight that study has. And then coming to here in next title, you can write, it is like odds ratio. So you can write odds ratio, that will appear here. And again, you need to do some modifications also, because this odds ratio, it takes, it calculates based on the log odds. So that's why it gives you as a 0. But when you have to present it, then you may draw this at 1. That will show again one line you have to draw at 1 here. So when you will draw that line, you have to draw one line between this 1, the 0 and 2. And then coming to this thing, forest plot. So if you come to forest plot, then it is like we have seen fail safe. This test we have learned that day, that this much study, that means 21 studies are needed. And this is significant. So if this is significant, then it is not this funnel, there is no publication bias. Again, we discussed that publication bias we only do when the number of studies are more than 10. So it is only 5. We are not going to interpret this because it doesn't make any sense. But again, that day we were discussing how to interpret the funnel plot. So funnel plot, basically there is a x-axis and there is a y-axis. On axis here it's the log odds ratio. On y-axis it is the standard error. You can, in the funnel plot, you can change also the in this case, no, you cannot. It is the log odds only. So this part, the higher, it starts, if you see this 0, this starts with 0. So the study having less, this is less standard error, and as you go down, the standard error becomes more. So studies who are at the top, they are having less of standard error. That means they are more precise. Studies which are at the base, they are having larger standard error, so they are less precise. And if you see the width, these width, so this shows up till significant. That means this gray area is showing the studies with insignificant result, and up till this bottom it shows you the significance, and this middle line, it shows you the effect. That means the log odd. So it is 0.7. So this value, this vertical line, it is at the level of 0.7. So that's why you can see that yes, there are study with a positive this thing also, this side also, and this side also. Although this is not the classical example, I said that to interpret this, the study number should be more than 10. But again, just for academic purpose, if you see there's one study which is lying outside this significant, that means this study was not significant. Without any significant finding, these 4 studies were significant, but again, few are reporting the negative result, few are reporting positive result. So you can say that yes, it's kind of evenly distributed, not so much. That's why many times if you see that this is a visual plot, that means a subjective assessment on the basis of visualizing this funnel plot. There's an objective way also, which we have seen, like Egger's test of regression or the other Begg-Majumdar rank correlation test. So they are more like they are objective way of determining. And if the p-value is not significant, that shows that there is no publication bias. So this was regarding this 2x2 table or the dichotomous data in case of this meta-analysis. Coming to, so these were the 2 from the exercise which we did. The rest we are showing it, and all that is a dummy data. That means those 2 outcome variable we did not see in that paper from where we have drafted this whole workshop. But for demonstration purpose, we have created that data set, and we will demonstrate the other 3 effect measure, which is the correlation coefficient, then on the effect size, and then one on the hazard ratio. So I'll show you on the other 3. Let me first read out the question. So if you see the question, this is the hazard ratio. So if you see this is the background. Again, if you see, this was my background, like to synthesize the available evidence on time to recovery study. Since it is not a time to event, but you know that hazard ratio is a effect measure in case of survival studies, where we measure the time to event outcome. So time to recovery studies, they often report hazard ratio comparing the probiotic versus standard care. And meta-analysis, if you see the review question, what is the review question? Like, does probiotic supplementation improve the time to recovery in children with acute diarrhea as compared to the hazard ratio, this standard treatment? And objective is to demonstrate the this how to conduct meta-analysis. So first we'll see we have got the hazard ratio and its confidence interval. I think before that, let me take this session on, there's a session on effect size. So probably that is needed before I go to hazard ratio, because hazard ratio is again a effect size. So let me take that, because then I'll tell you what is the upper confidence interval and how do we calculate it. Let me close these two. So this is only a very only we are only touching the effect size in although this effect size is a very huge topic, and you may go and learn this more, but again for meta-analysis purpose we are only summarizing what is this effect size, what all you need to know in if you are performing meta-analysis. So basically effect size, let's see this with one analogy. Why do we need to convert everything into effect size if the measure of associations are quite heterogeneous? So imagine this is one scenario, like hypothetical scenario, or you may have faced this scenario also, that you are trying to compare the price of a cup of coffee in different countries. But you know that each country, they have their own currency. And in India, what do we do? Every currency we convert it in the INR, which is the Indian National Rupee. And then we see like how much it is costing to us. So in this case, you can see here in the first column, there are names of the country like Japan, France, UK, India, Brazil, Australia. And then next to that column, it's the name of the currency of that particular country. And then the price of the one cup of a coffee in local currency. So if I ask you like which is the country where this price of this coffee is the highest, so what will you answer if you see this table? Yes, all of you please answer. Yes, Priyanka is right, South Korea. Okay. But this is only of number. We don't know. Like if I have to pay, whether it will cost more to me or less to me. So now what will I do? If you see the price in US dollar, and because I have converted now everything to US dollar, because that's the standard way. Everywhere in the global this thing, we convert all the currency into US dollar. So if you see the US dollar now, what will be your answer? Where the price is the highest? Yes, Switzerland. True. So now your now your answer has changed. Why? Because now you have converted that. So that's the overall concept of effect size. So in effect size, what is there? Like someone is measuring in the correlation coefficient, some person is measuring it in the form of odds ratio, risk ratio, and people are measuring it like maybe proportion or maybe as a mean, standardized mean. And now if you need to compare everything into using one this thing like we have done with this currency one, you need to convert everything to the effect size and then you can compare. So this is like effect size. So how do we, like in this case, in case of this probiotic example, so suppose if you are conducting a meta-analysis of this probiotic on the duration of diarrhea. So I've got several studies, but each studies, and you have seen, like you must have faced this, like they report the outcome in quite a number of different ways. So one study has reported the mean difference of the duration of diarrhea between the probiotic group and the control group. The other study has reported like percentage of people having a reduced diarrhea, the way we have seen in the dichotomous data. The other third person has reported maybe a Bristol stool scale in a 1 to 10 scale. There was a reduction in score of that particular scale. And then probably one person might show it, like the study is on the proportion, it is not on the intervention study. What proportion of children they have, I'm not children, means their caregiver has used diarrhea, and proportion of children who has used this diarrhea within 4 days in each group, like we have seen with the dichotomus. So all the people, there are researchers and everyone has reported these way, like with a different way. So how will you compare when you have to combine these results, and how can we make these results comparable? So for that, you need to know the concept of effect size. So there are various formulas for effect size. We will give you those formula right now. What we are doing, like we are telling you, you should first, on the first step, you should try doing it, taking the studies which have reported the similar measure. First you do that, and then again the next step is when you need to convert all these into the single effect. But that is a little one step ahead. That's why we are not covering a conversion of each into a different effect size, but we are showing the studies reporting the similar effect size, and then uh, showing or summarizing the pooled effect of that effect size. So what is the effect size? So basically effect size, that this is a quantitative measure, which again, basic aim is to see the association, or to see the association between the two variables, whether it is hazard ratio or odds ratio, or it is correlation. Correlation is also effect size. So in all these cases, you see the association between the two variables, and purpose is basically it allows the researcher to compare the result, because if you don't use this effect size, you cannot compare the way we have seen the example of coffee. So to make the comparison, you just make everything into effect size, and then you can compare, even if the different researcher, they have used the different outcome measure in their studies. So it helps you in the standardization of this your metric or the outcome which you are measuring, and that's how then you can make a meaningful interpretation, because then whatever you will understand and you will convey it to the scientific community, that will make some sense, because you have converted everything into a effect size, and now the studies are comparable. The diverse nature of the studies, if you convert them into effect size, the studies are comparable. So there are various common types of effect size which are there in case of a meta-analysis. There's a mean difference, which we have seen in case of the example, the diarrhea. Mean duration of diarrhea, mean duration and standard deviation. Then if you divide it with the standard deviation, there's a standardized mean difference. That is, again, that can be one measure. Then there's a odds ratio, which we have seen just now. Then there's a risk ratio. So the odds ratio, risk ratio, or risk difference, three are there in case of a dichotomous. Then if it is a time to event analysis or a survival analysis, then there is a hazard. And if you are doing like correlation studies, then it is the correlation between the two, Pearson's correlation. And then if you are like measuring the prevalence of something, like if you are measuring the prevalence of caregiver using the probiotic, then it is the proportion is also effect size. So how will you choose the right effect size? So first you see the nature of the outcome. Whether your outcome is a categorical, like if you are measuring it like mean duration, then it is a continuous nature. Then you need to take the mean difference. So whether your outcome is a categorical outcome or is a continuous outcome, if you are just measuring this thing, some continuous outcome, then again it will be something like correlation. Or if we are measuring time to event, then it will be your hazard ratio. You have to see the study design also. Like some study design, in case of intervention studies, it may be a risk ratio, it can be a odds ratio. Or if you are doing like a cohort study or longitudinal study where you have got the data of time to event, then you can perform you can take hazard ratio also as a, or if you are doing some association studies, if you have got correlation, then it may also be like a correlation or the R as a effect size. So heterogeneity again, because if the studies, they are using the different metric for this measurement, then again it will be quite heterogeneous. So if the studies, they are using the different scales of measurement, then also you can use this effect size. So so many times you have to do the transformation. So what are these transformations? So basically you do the log transformation. So certain effect sizes, like in this case, odds ratio, you have seen that it takes the log odds. So you have to transform the variable, especially if it is a proportion also, or hazard ratio, or even the odds ratio. That software does, and you have to like transform it into the this thing, log odds or the log hazard ratio, to stabilize the variance, because the studies are quite heterogeneous. We see that heterogeneity because each study is having a different picot, so there will be heterogeneity. So to take into account of that heterogeneity, you do the log transformation and you normalize the variance or you stabilize the variance. And then after pooling, you do the back transformation, the way we have done with the odds ratio. After it pools the result, then what it does, there is an option in JAMOVI, you can click that and it will back transform that log odds ratio into odds ratio for the better interpretation and understanding. How will you interpret this pooled effect size? So this pooled effect size basically, that summary statistics, it tells you, and the confidence interval of that summary statistics, it tells you the precision of your study. That means if the confidence interval is narrow, your pooled estimate is precise. If the confidence interval is large, the pooled estimate is not that much precise. I think here we have told them the formula. Now, how do we calculate this? That I could not find that slide. Upper minus lower.
Conversion of log, no, madam.
Conversion of log, and again, how do we calculate the from log transformation the variance? Let me see. I wanted to take that. Let me see this. No, that we have. Give me some time. Let me check.
What is this risk difference, ma'am?
Risk difference is risk in intervention and risk in case of a standardized group. Like I said, now you have to first see the. Let me just a sec. I'm coming. Okay, let me close this. I'll tell you when meta-analysis of proportion. Okay. So, okay, yes, this is again, let me take. No, this I need now. Here, this formula I need to tell them now. That's why this is needed. But again, this now, upper and lower. So for that, actually, I wanted to tell you this difference. So Zubapriya, this risk difference is again difference in risk. What is actually relative risk? So if you know the relative risk, incidence in exposed and incidence in non-exposed, you just see the absolute risk. When you take the ratio of these risks, it is known as the risk ratio. And difference is when you take the difference of these two. That's the risk difference.
Okay, ma'am.
So, no, before that, let me tell you. So I wanted to tell you this formula. I'll tell you this. So whenever you have to, because in case of this hazard ratio or effect size, you have to calculate, in case of a JAMOVI, you have to calculate the standard error. So how will you calculate standard error? This I wanted to tell you because you will need this. So whenever you tell report your confidence interval, how do you report? So basically you say that confidence interval is mean plus minus 1.96 multiplied by standard error. That's the formula for confidence interval. And what is the upper? These are basics again, but you should know this. So what is the upper confidence interval? Because you need this when you will calculate this standard error. So what is the upper confidence interval or the upper level of this confidence interval? When you just plus this 1.96 times into SE, many people do it 2 like, but actually it is 1.96. So mean plus 1.96 times standard error, that is your upper confidence limit. And mean minus 1.96 times your standard error is your lower confidence limit. So what will be the full width of this confidence interval? So upper confidence interval minus lower confidence interval will be your full width. So it will be like if you just replace this mean plus minus 1.96 into SE minus in the bracket, it is again the same this one. So I have taken this from here minus this from here. And then if you like equate this, your value of standard error will be upper confidence interval. So this is your final formula. If you don't want to remember this, that's okay. but you have to not remember, you just have to put that in the either in Excel or in JAMOVI. Because what happens in the effect size, they give you the effect size like odds ratio and the 95% confidence interval, or the hazard ratio and 95% confidence interval. In generally, in those paper, you will not find standard error. So for standard error, you need to calculate this, because if you have to do the meta-analysis using effect size, the standard error you need to like calculate this in JAMOVI, because that's the variable which will be entered in the JAMOVI interface. So remember this, what is that? So you need three, first, whenever we enter the data, we'll see the data set. You will have to enter the three things. The summary estimate, like maybe odds ratio, or maybe the hazard ratio, or maybe the risk ratio, the upper confidence value and the lower confidence value. These three you need. And then this standard error we calculate. Either you can do it in Excel or you can do it in JAMOVI. What you do, what you do, upper minus lower divided by 2 into 1.96. That's how you do. So this I wanted to tell you before I was about to tell you this hazard ratio. So I have read out the question. So I'll go to this. This is the hazard ratio. This is again the Word file. So first I'll show you the Excel sheet. So again, this we have not seen in all those studies. This is just a dummy data. Remember, this is the dummy data. These are not the actual data. So right now, if you see, these three I have taken from the studies. The hazard ratio, like I was telling you, the lower confidence interval and the upper confidence interval. And now how will you calculate? Either you can do it here in the Excel. You have to first calculate the standard error. So standard error, if you have to calculate, how will you do that in Excel? Again, just make equal to, then upper confidence interval minus lower confidence interval. So this minus this, and then again you can divide that with 1.96 into 2 becomes 3.94. So I will write like 3.94 and press enter. So you will see that, okay, maybe this minus is there because in my case it should be the upper minus lower. What I did, D2 minus C2 means, so that's why it is coming as minus. Otherwise, like if you do the upper minus lower, then it will be the same. And then you do the double click. So this value will be the same except for like minus sign. This is your standard error. The way we have told you, like it is the upper minus lower divided by 3.94. And what is 3.94? It is the 1.96 multiplied by 2. And here you can take the log. So how you take the log? Again, log you can take is equal to, if you write like natural log and take this and select this variable, this one, HR, because I am taking the log of HR. Select this and then press enter. So it will be your natural log of your hazard ratio. Similarly, your log of all these two. These you can take on the Excel. Otherwise, in JAMOVI, actually what happens, even if you enter the raw values, it gives you, because JAMOVI does that in the background. So for JAMOVI, you don't need to do this log conversion. So there, if you see, but we have just told you how to do that. But this standard error you have to, this log is again, Bhavna, you don't like just click plus and then write a log. It is in the Excel. equal to and select this and then select the variable. Like if I'm doing it for upper CI, select this and then press enter. So it will calculate. So in Excel, equal to and then select log ln. And then a bracket will come, you select the variable and press enter, it will come. And then again, once it is there, you can double click this, it will be populated. But again, in JAMOVI, you don't need, because JAMOVI generally, if you see, they do it in the background. So I'll just show you in the JAMOVI. So this was the hazard ratio. This is the lower confidence interval, this is the upper confidence interval, and this is the standard error. So if I like, how will you do that? You have to enter the here in the, you have to select measure, select effect sizes and sampling variation, because now I'm doing all these log odds, hazard ratio, these are effect size. So effect size, you need to enter the study label. So I'll enter the study label, this one, and then effect size, and effect size is your HR. So I'll enter the HR, and then upper and here, instead of upper and lower CI, you need to enter the variance or standard error. So I have to, that's why I need to calculate that standard error. So I'll enter this standard error 1 here. So it will give you the, and random from model option again the same. From here, instead of sampling variance, you need to select the standard error because I am doing it on standard error. So select standard error, model estimator, random effect model, DERS Sigmund layer. This I have selected. Moderator analysis I am not doing. And if you come to the plot, click on this plot if you want prediction interval. Since you all know now, that's why I'm clicking. You can click on this model fitting weight and you can see like what you want in the funnel plot. If you see this y-axis, you can have, instead of standard error, you can have these options also. But this come in the effect size. The other options, it was not coming. But in case of effect size, you can change this. But since we are doing it on the standard error, I have clicked this. I have clicked this. And then you can go to this publication bias. This to all, it was clicked. So nothing to do. Now coming to the interpretation. If you see the intercept 0.87, so that is the value of hazard ratio. And it's the upper and hazard ratio of the pooled estimate. And this is the upper and the lower upper and the lower bound. And then heterogeneity statistics, if you see the I-square value, this value of tau, what was the tau? Tau was the standard deviation of the true effect size. That means between study variation. What is tau square? Tau square is basically your variance, because whenever you square the standard deviation, it becomes variance. So tau square is the variance between study variance. So it is the both these tau and tau square is the between study variability or the heterogeneity. This I square is the again measure of heterogeneity, and this is 68. That means there is a significant heterogeneity. And here also, if you see the value of this Q statistics, the p value of this Q statistics, then this is here. This is significant. So you can say that there is a heterogeneity, significant amount of heterogeneity. This is your funnel plot, forest plot. And in forest plot, relative weight, I think I clicked that, but this is not showing it up. Model fitting weights. You can write here hazard ratio. Prediction interval. Model fitting weight. So now it is giving, you can see, this is the weights it is giving. All studies, if you see, since it is a dummy data, so you can see all studies having like 8, 9, almost equal weight. And this is your prediction interval, these two. So what is prediction interval? Prediction interval is regarding your future studies. If any future studies will be conducted, so the value will lie between these two ends. And then if you come down, again, this doesn't give you write-up. So in case of if you are using effect size, it doesn't give you the write-up. These are the publication bias assessment tests. So these are the two. So if you see, these two are significant. Kendall tau is significant, Eggers regression. This is important, Eggers regression. This is also significant. That means there is a publication bias. If you see this visual plotting also, again, there are studies, if you see the number, again, there are 4 studies having this towards this less than 1 hazard ratio, and there are 5 studies having more than 1 hazard ratio. And there are 2 studies which are outside this. That means they were not significant. So again, this funnel plot, it indicates some amount of symmetry, if you see. That's why you will see that here. Again, and in this case, you can comment. Let me see how many studies are there, because for funnel plot, you need more than 10. So 3, yes, it is more than 10 studies. So you can comment on the funnel plot, because for that, you need more than 10 studies. You don't need to see this equivalence test. That's not needed. Actually, it gives you by default, but it is not needed. This one equivalence test. So you need to comment only up till this point. So this was regarding the hazard ratio or the effect size. Because this will be same for everything. This is for effect size. So if you are using odds ratio as a effect size, or hazard ratio as a effect size, or risk ratio as an effect size, it will give you this. And whatever you put as a entry, it will give you here like that. That means it is giving you the odds. This is the hazard ratio. This is not the log. This is the hazard ratio. Log we only use when there is there's a large amount of heterogeneity. Then you can use the log. You can use this also. Both are okay. Because here, there's no way you can use this back transformation into this log, the way we have seen with the odds ratio. Then coming to your another one, which is the correlation coefficient. So next one is your correlation coefficient. So if you see this correlation, what will be your research question or the review question? So here, if you see how there are several randomized trials which reported the mean difference in the diarrhea duration between the intervention and control group. And some studies, they have reported the correlation coefficient between the probiotic use as a continuous or ordinal exposure and the duration of symptoms or recovery time. So again, it is showing like few examples are there regarding numeric terms, how you can take the probiotic like doses. You can take the doses as a continuous outcome, or duration for how many days they have used this probiotic, or the cumulative days, total number of days they have used for the probiotic. And this again, you can use their frequency. You can make it categorical. They are using it rarely or sometimes or regularly, or you can measure their adherence score if you have got something to measure the in the adherence scale. And then the review question would be like, what is the pooled correlation between the probiotic use and the duration of diarrhea in children under 5? And this was the data. Again, this is the dummy data. So these are the studies. They are the total number of children in each study, and you need a correlation coefficient. So these 3 measure you need. And if there is a negative value, that means negative correlation. That means if you increase the correlation, if you increase the probiotic use, the duration of diarrhea will be lessened. coming to the JAMOVI sheet. This is your correlation. So these are the numbers you can see. We have got this R and the total number N. And how I'll show you on the Excel also, because you need to convert it. So let me show you the Excel of this. So in Excel, this R you will get and this N you will get. This we have calculated it. So formula for this is, if you see, this is like 1 minus R square divided by square root of N minus 3 and then N minus 2. That's the formula. And then this Fisher is again, it is using this formula. This is 0.5 multiplied by log. In the numerator, you take 1 plus R, which is the correlation coefficient, and in denominator, you take 1 minus R. This is for the, you are converting this R into Fisher Z. This is also used many times, and this is your, what you do, you take this standard error of Z square, like Z square of this standard error, which is calculated by 1 divided by root and of N minus 3. This is again all the formula. We have given you these sheets. You don't need to remember this. Okay. And this we have used, like written here, the strain type, like lactobacillus. If you have to do moderator analysis, which we are not showing it, like, but if you want to see the pooled effect between the lactobacillus group and the Saccharomyces group, then you can use this. But again, JAMOVI doesn't have this function of categorical outcome. And this is the continuous outcome. But in RevMan, you can do this. In JAMOVI, you can use continuous outcome, but in RevMan, you cannot use the continuous outcome. So these are two different, one advanced version. But again, I think you should not go into these two types. Right now, let's restrict to the basic ones. And if you come here in the correlation, JAMOVI does it automatically. I mean, let's see how it does. So you click on this major, click on this correlation coefficient. So here it only needs the correlation. I mean, right now I am entering this raw value, this correlation, and then this N. And then study these three. We have shown you these three. In the background, it calculates using this. But in JAMOVI, you don't need to enter this standard error or this Z square. We have shown you in this case, because I am considering this correlation as an effect size. So that's why I have entered this correlation here. So correlation N and then study variable. If you see the model option, again, I will use this as a Darsamuin layered. Here you can see it is transforming. Fisher R to Z transformed correlation coefficient. JAMOVI does it. So you don't need to transform it. Okay. But if you click this, raw correlation coefficient is also there. And then moderator analysis we are not doing. This is the like test and confidence. For that I'm using this Z test. That's the standard one. 95% confidence interval. If you come to plots, this is your summary estimate. You can click on this model fitting weight and you can show the prediction interval also. And then funnel plot, it will show automatically. You don't need to wait for some time. In case of correlation coefficient, it gives you the write-up. So intercept is 0.2, 0.23 with a standard error of minus 1.17. And that's why you see that this summary statistics, it is not significant. That means because it is crossing 1, I mean less than 1, minus is also there. Seeing the heterogeneity, if you see this I square, it is very heterogeneous. It is a 96. So ideally in this case, you should not perform meta-analysis. If such 96%, that means it is quite heterogeneous. Again, these are the same output which we have already read regarding the influential point and the Cook's distance and regarding how it calculates. And then here it tells you like none of the study. So there is no point doing the sensitivity analysis because none of the study is showing a Cook's distance which are like influential or the standardized or the studentized residual. So this is for the correlation coefficient. Okay. Okay. So right now it is 11:40. So we may have a break of 5 minutes. All of you please come back after 5 minutes and then we'll go to the breakout room. Okay. Of 45 minutes. Okay. So this Excel. Okay, I'll repeat Dr. Ponudhali. Actually, this sheet is there. If you see this, formula is there. So nothing, you need to just, if you have to calculate this Fisher's, first let's start with standard error. So standard error is, how will you calculate it? It is 1 minus R square. You can see it's written 1 minus R square divided by square root. But again, like I said, if you see the JAMOVI interface, let me show then we should not have given that will create. In Revman, there is a calculator. So there also it is not needed. I think for now, it will create confusion. Dr. Ponudhali, because in JAMOVI, that we have given you how it does in the background. That means how it is doing this Fisher R2Z transformed correlation coefficient. In the Excel, we have given the formula, but actually you don't need to do it. Why? Because you see here you need to enter only these two values, the R and the N. You don't need to do these calculations. So I think for this, let's not dig deep into that. This Excel sheet is there with you. You can explore it because in Revman also, there's a calculator. So if you enter your raw R and N, it calculates. So anyways, you don't have to calculate it. Okay. So it's not needed, I guess. So don't go, I think, first learn these, how to enter it in the JAMOVI. And then you may see that Excel or we may discuss towards the end.